In today's lesson, we are going to look at what is known as the Z-test for a hypothesis of a population mean, or for hypotheses about population means. Now, just like when we saw confidence intervals, we looked at the general information for a confidence interval, and then looked at several specific cases. That's exactly what we're going to be doing with hypothesis testing as well. And so this is just the first specific use case for hypothesis test that we're seeing. So in today's lesson, we want to understand how we're going to test population means when we have approximately normally distributed populations. Okay, so I want to point out that all of my past discussion about confidence levels is going to apply for hypothesis tests, and in fact, I'd emphasize it even further for hypothesis testing. The general framework of testing hypotheses is very much worth knowing and understanding and sort of deeply getting why we're doing each step of it. Each of these specific procedures will come up often enough, but I don't want you to have to try to memorize these as though they are separate tasks. We're all doing the same steps, and the same steps are being motivated by the same considerations. And so because of that, if you understand sort of the underlying philosophy of what hypothesis tests are doing, then you can sort of use that for any of the situations that we might be looking at. In the test today, what we're going to be doing is supposing that we have a normal population and that we know the variance, but we don't know the mean. Okay, so it's sort of this unrealistic scenario again, but we're going to start with that. We're going to test the hypothesis that h naught mu is equal to mu naught for some fixed constant against the alternative that it's not equal to this. Okay, now I would point out that we could also be testing the hypotheses h naught mu is less than or equal to mu naught versus it being greater than, or h naught is mu is greater than or equal to mu naught versus being less than. Notice that in the null hypothesis, we always have the equal sign, right? We need that sort of equality value. And it turns out that sort of any of these three hypotheses are going to be tested in basically the same way. It's just going to change how we compute the p-value ever so slightly. Okay. We've seen that the sampling distribution for this statistic is going to be a normal 0, 1 under the assumption that the null hypothesis is true, right? And so in particular, if mu equals mu naught, then x bar minus mu naught divided by sigma over the square root of n is going to follow a normal 0, 1 distribution. Now, if this is the wrong mean, then this is not going to be the case, right? But if that mean is correct, then this distribution is going to hold exactly. We do not need this to be a normal population. What we need for this to be is that this test statistic is going to be normally distributed. And so just like when we were forming confidence intervals and we saw that occasionally we could use the exact same procedure when normality came out in another way, the same thing's going to be true here. Right now, we'll assume that it's coming from a normal distribution, but we just require this test statistic to be normally distributed. And the question that we want to answer is, how do we find the p-value? And so remember that the p-value that we're looking for is the probability of observing at least as extreme if h naught is true, right? And so the question is, if we observe some value of z, right? So we take z equals some little z, what's the probability that we observe something which is at least as extreme as that is, assuming that h naught is the true mean, okay? And so the easiest way that I can think about doing these is through these diagrams, right? And so we'll sort of annotate them as we go, but they're all in the slides here as well. So let's assume that we have our little standard normal distribution here. And it's poorly drawn. It's better drawn on the slide, but that's okay. So we're going to have 0 here, right? Because, or it could be centered at mu naught, but if we've already sort of centered it using that standardization procedure, then it's being centered around 0. And we're assuming that we observe some value of z, right? Now, of course, anything that's above z is at least as extreme, right? But also, if we were to look at the negative version of z down here, because our alternative is mu is not equal to mu naught, then anything that's down in the negative tail also would have contradicted our null hypothesis, right? And so our p-value is, as a result, going to be the combination of these two areas, right? So we can fill in the upper tail, we can fill in the lower tail. The p-value is going to be the sum of those two areas. And so, in particular, what that's going to mean is that we want the probability that the absolute value of our normally distributed variable is at least as large as the magnitude of the statistic that we observe. Now, because we're dealing with a symmetric normal distribution, we can actually sort of start working this out, and we can say that that's those two tail values that we have here, right? So that the probability that it's larger than the absolute value of z plus the probability that it's less than the negative absolute value of z. So if we add those two areas together, that works because of the symmetry of the distribution. And so now we could use the tables, the critical values, or the statistical software that we've seen in order to actually get values for these normally distributed statistics. Now, if our null hypothesis is one-sided, so we had instead h naught mu less than or equal to mu naught, then observing something down here doesn't contradict the null hypothesis, right? And so in that case, only this upper tail would count. And so we don't actually take both of those. We only take the probability that it's larger than what was observed there. So if we're testing mu greater than or equal to mu naught for the null hypothesis, then we only consider the lower tail. If we're considering that the null hypothesis is what we displayed here, then we only consider the upper tail. I think it's normally helpful to simply draw out your rejection regions here, and then you can start calculating the p-values that you end up coloring in on the diagrams that you draw out. In these cases, we're not taking the absolute value because it would only matter if we're in the right area of the tail. So if we are using critical values instead, then we would simply look up those values corresponding to 1 minus alpha over 2 and alpha over 2, and then do the comparison against the critical values. So, in summary, if the sampling distribution is going to be approximately normally distributed, we can use the test statistic that we've been used to using and a normal 0, 1 to run the hypothesis tests. The rejection region is going to depend on whether the alternative is one tail or two tail and which tail it is. And like I said, you should probably just draw out that graph and then say, where are we going to have evidence against our null? And then adding up those regions is going to give us the specific p-values. So in the coming lessons, we're going to keep looking at different specific iterations of this hypothesis testing, and I hope to see you all in those lessons.